Welcome back to Math 124, Introduction to Statistics. Today we're going to talk about a hypothesis test for a difference in proportions. Let's consider the case of a produce department manager who is considering tomato suppliers. He has tomato supplier number 1 and tomato supplier number 2. Unfortunately, it is always true in the course of bringing tomatoes to the grocery store that some of them are rotten. And we will let X stand for the number of rotten tomatoes in a given shipment of tomatoes. The question is, does one of these suppliers ship more rotten tomatoes than the other one does? Who might be the better supplier? To answer this question, our grocery manager will take a sample from each supplier. And the number in the sample from supplier number 1 that are rotten, the number of tomatoes that are rotten, will be X sub 1, and the number in the sample taken will be N sub 1. Likewise, for our supplier number 2, the grocery manager will take a sample of N sub 2 tomatoes and record as X sub 2 the number that are rotten. And now we can calculate the proportion in each of these samples by simply dividing the number of rotten tomatoes by the number in each sample. Okay, so that will get us our P sub 1 hat and our P sub 2 hat. So our manager wants to perform a hypothesis test to see if there is a difference in the proportion of rotten tomatoes between the two suppliers. So our null hypothesis will be first that there's no difference. We're looking at a difference in proportions. So I'm going to write my null hypothesis as a difference in proportions. And if there is no difference, we would put that equal to 0. Your null hypothesis is still always a statement of no change, statement of equality and no change. All right, and let's look at the difference between the two proportions. Oops, I forgot my sub 2 in that first statement of the null hypothesis. This is my alternative hypothesis, and we'll just say that we'll test to see if there is some difference. In other words, the difference between the two proportions is not equal to 0. We have stated our hypotheses. Now we need a test value. Because we are working with proportions, it will again be a z sub 0 symbol for our test proportion, and we will be returning to the normal distribution to obtain our p-value at the end of this process. Our test statistic will still be equal to the statistic of interest minus the null value divided by the standard error. But since we are working with a difference in proportions, the details of the formula have changed. In fact, there is one more calculation that we will have to do. And I will give you an example that actually has some numbers in a little bit. But the other value that we need is not P sub 1 hat or P sub 2 hat, but just P sub hat, the proportion of all the tomatoes in both of these samples that are rotten. So we will add the number of rotten tomatoes in sample 1 to the number of tomatoes in sample 2 and divide that by the total number of tomatoes in each sample. Let's start writing our formula. We need the statistic of interest. What are we interested in? The difference between the two proportions. So that is our statistic. P sub 1 hat minus P sub 2 hat. The difference in the sample proportions. And what is our null value for the sample proportions? We think it's 0. Okay, at least the null hypothesis is that the difference is 0. So that makes the numerator simpler. Unfortunately, the denominator is another story. Okay. Now, when we were dealing with proportions, we had proportion, right, times 1 minus the proportion divided by n. except we have two proportions now. And the proportion we are actually interested in is the proportion of Rotten Tomatoes overall, this p hat that we would calculate here. Okay, so p hat, no sub-values, and also that p hat shows up here. But the n does have a subscript. It has a subscript of 1. Then we are going to add to that, still under this radical, the same numerator, p hat times 1 minus p hat, and that is divided by the number in our second sample. So it is a little tricky there. You'd either think we would drop subscripts completely or we'd keep them, but we don't. We use the p hat, which we calculated were all the Rotten Tomatoes divided by all the tomatoes in both samples, the sum of them. That gives us our p hat. It goes here, 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 and here, and we're dividing by the number in the first sample and the number in the second sample. Now, sometimes there's some algebra done upon this formula to make it a little bit easier to put in the calculator, but I like leaving it in this format because it is more similar to what we have worked with before. And I think that makes it easier conceptually to remember what we are doing. So let's look at an actual example. So let's say the number in sample 1 is 46 and the number in sample 2 is, 52. The sample sizes do not have to be the same to perform this type of hypothesis testing. And in the first sample, there were 4 bad tomatoes, rotten tomatoes, and in the second sample, there were 6 rotten tomatoes. What were the two proportions? Well, 4 rotten tomatoes divided by 46, well, that would be equal to 0.087. Then 6 over 52, I'm going to have to make some room here for this one, equals 0.115. It looks like the second supplier is supplying a larger proportion of rotten tomatoes, but could that just be happening by chance? That is what we have to discover. And we have not yet calculated everything we need to find our test statistic. We still need p hat. So we're going to take 4, which is x sub 1, and we're going to add to that 6, which is x sub 2, and we're going to divide that by the sum of the number in our samples, 46 plus 52. That gives us 10 divided by 98, which is equal to 0.102. You may notice that I am going ahead and rounding off my decimals to the thousandths place. That's to make it easier for you to see where I am placing them, where they belong. So for now, as we're just getting into this topic, let's go ahead and do that. Let's round our proportions to the thousandths place and then plug them into the formula. So here we go. We have our p hat sub 1 of 0.087. We are subtracting from that our p sub 2 hat, which is 0.115. And we're subtracting from that 0, which I don't even have to write. And then in the denominator, we have a lot of stuff in the denominator. We have our p hat, which is 0.102. And that goes in here as well. But that takes up a lot of space. Let's go ahead and do this subtraction. 1 minus 0.102. That's just going to be equal to 0.898. And then we divide that by our n sub 1, which is 46. Then, still under the radical, we have to add our, once again, p hat times 1 minus p hat divided by the number in our second sample, and that number is 52. So all of that has to be calculated. Once again, I'm going to go step by step, and I'm going to be introducing some rounding error because at each step I'm going to round it off to the thousandths place, but we're just getting a hang of this right now. So the difference between the proportions in our numerator is negative 0.280. In our denominator, I'm going to evaluate that first fraction. 0.102 times 0.898 divided by 46 gives me 0.002, and that is rounded quite a bit. Okay, and then for my second fraction, I have found the value 0.002. And these two values round to be the same because our samples are really quite close in size. When you are working with samples that have a large difference in sizes, you will not get the same values here. And then finally, when we evaluate, we get negative 0.443. That is our test value. Let's take it to stat key. Here is stat key. We will be moving to the theoretical distribution, to the normal distribution. And we are performing a two-tailed test. Our test value of negative 0.443 goes to the negative here. So negative 0.443. Hit enter. And what is our p-value? Now, we have a p-value right above our test value, of 0.329, but remember this is a two-tailed test. We have to multiply that by 2. We have to account for all of this area and all of this area. So what we're going to be looking at is, let's get rid of stat key here because we have our p-value. And our p-value was 0.329 times 2. And that is 0.658. Now, I did not give you a significance value, did I? And we said if it's not given, you can assume that it is a significance level of 0.05. It doesn't really matter what it was because it's going to be really hard for this large a p-value to beat any level of significance. So we do not have a tiny p-value. We do not reject the null hypothesis. Do not reject H sub 0. Okay, what does that mean? It means that as far as we can tell, there's no difference between the suppliers. There's no evidence that one supplier is better than another. Let's move through one more example about eating organic, or at least let's talk about fruit flies eating organic. If it's good for them, maybe it's good for us. Let's look at the results for samples of fruit flies that either ate organic or conventionally raised potatoes. In fact, let's go ahead and not call them sample 1 and sample 2, but instead sample organic and sample conventional. So therefore, to make room on the screen, let's just start listing our statistics that we're going to need to use. So starting with our sample that fed on organic potatoes, this was a sample of 500 fruit flies. And for our sample of conventional potatoes being devoured, we also had 500. So you can run these tests with different numbers in your samples or with the same. And out of the organically fed fruit flies, we're going to look at how many of them were still alive after 20 days. 250. Meanwhile, of those fruit flies eating conventional potatoes, 130 of them were still living after 20 days. So let's figure out the proportion for the organically fed fruit flies, the ones who survived, and the proportion of the conventionally fed fruit flies who survived more than 20 days. So the number who survived, 250, divided by the number in the sample, gives us our proportion in each case. But of course, 250 divided by 500 is equal to 0.50, and 130 divided by 500 is equal to 0.260. And finally, we need to calculate the pooled proportion. In other words, how many fruit flies in total from both groups survived more than 20 days. And then we have to divide that by the total number in the groups, which is 500 times 2, or 500 plus 500, or at any rate 1,000. So our pooled proportion is going to equal 0.380. So our null hypothesis will be not that fruit flies live 20 days or anything of that sort. We are working with proportions. So our null hypothesis will be that there is no difference between these proportions. If we subtract the proportion of fruit flies that lived greater than 20 days eating conventional potatoes from the proportion of fruit flies who lived greater than 20 days eating organic potatoes, we should get 0. That means our alternative hypothesis, I think I'm going to start doing my A's this way so you can see what they are better, will be that, which one are we looking to be bigger here? Which one do you think it might be? We think it might be organic, right? So that if we have a larger proportion of the fruit flies eating organic, we subtract from that the proportion of fruit flies eating conventional potatoes, we would expect that to be greater than 0 because the first value is greater than the second value. As a reminder, another way these hypothesis tests could be written is this. You could write that the proportions are equal for your null hypothesis, and your alternative hypothesis could be that the proportion of fruit flies who lived greater than 20 days and ate organic was greater than the proportion of fruit flies who lived greater than 20 days while eating conventional potatoes. But I prefer using the first method I wrote down here because it helps remind you that we are dealing with a difference in proportions, in case you should ever forget that. Now let's get our test value. There is the formula for our test value. Let's put in the numbers we actually have. The proportion who ate organic minus the proportion, well, who lived more than 20 days eating organic or conventional, divided by the square root of, okay, our p hat is 0.380. I'm going to do something here. I'm going to go ahead and calculate over here what 1 minus p hat is equal to, or 1 minus 0.380. That is 0.620. So that's what goes here, divided by the number of our organic eaters, which was 500. And then I'm going to add to that the same numerator, our p hat times 1 minus p hat. Ooh, running out of room there. And that's divided by the number of our conventional eaters at the beginning of the experiment. And then if we calculate all of that, I will leave it to you, but you should get 7.818. That is a Z value. That is a huge, huge value. Let's take it to stat key anyways. So once again in stat key, we are going to use a normal distribution. We are now looking at a right-tailed test. And we need to reset our cutoff to 7. Let me get to it. 7.818. Enter. Wow. Look at how the graph has squeezed together there so we can get all the way out to 7.818, and it's practically 0. So we really didn't need to go to that normal distribution to figure this out because we had such a high test value here. There is strong evidence that we should reject our null hypothesis. And let's state this conclusion formally. We find very strong evidence that the proportion of fruit flies still alive after 20 days is significantly higher for fruit flies who eat organic potatoes than it is for fruit flies who eat conventional potatoes. And that concludes our lesson for today. Let me know if you have any questions, and I will see you in class.